All right, chemists, let's get started today. All right, so we are going to start chapter 5 here. The idea in chapter 5 is that we've kind of been neglecting this component of chemical reactions. We know that atoms themselves are, rearranging. We have to make sure that the atoms themselves, the elements, are balanced across the chemical equation on the reactants and products. So this component that we've been missing here is the idea of energy. Energy is involved in chemical reactions. You have witnessed this, all right? So the idea here, on Friday, I did our hydrogen balloon demo. So do recall from like the first day of classes where we did the hydrogen balloon demo, I'm going to constantly be referring back to that chemical equation or that demonstration in order for us to kind of think more broadly about the idea of energy involved in chemical reactions. We know energy is involved in chemical reactions. You saw it, right? You felt it when the hydrogen balloon went off. We know that hydrogen atoms, oxygen atoms, they rearranged, but there was also a lot of energy that came off of that reaction that you observed, you felt. And so the idea in your mind when you think of that chemical reaction that happened up here, the hydrogen balloon, we all cover up our ears and all of that because there's just so much energy that's given off. The idea that that reaction involves energy, you felt that energy coming off the chemical reaction, so that oftentimes has a negative sign associated with the actual chemical reaction that occurred, that the system itself is the balloon and everything in the balloon, and so that reaction lost the energy. You, as the surroundings, felt that energy coming off. So the big idea here with this chapter is we're constantly going to be wrestling with a negative sign and a positive sign. And so the idea is understand what your system is and how energy is being transferred into the surroundings and how you are observing that. So let's revisit chapter 1 where we briefly talked about energy, the two types of energy we discussed, kinetic energy and potential energy. We'll go into more detail about these ideas, but those same equations apply here. Kinetic energy, we can calculate it as 1/2 the mass of your object times its velocity squared. So this is energy due to particle motion. But since oftentimes we're working with a lot of particles, we have a large sample, oftentimes we associate kinetic energy with the temperature of the sample. So we'll constantly kind of be referring to this idea that the temperature of the sample is actually the average kinetic energy of the entire sample. So do understand that if the temperature goes up, we oftentimes see the particles moving faster within there. Then a new term that we talked about is potential energy. You might think of potential energy in terms of physics, but for chemists, we think about potential energy in terms of electrostatics, where we have attractions or repulsions, and that potential energy changes depending on the distance between those particles are from one another. We'll come back to potential energy. And the idea is that with potential energy in chemistry, potential energy is lowest when particles are attracted and close together. Just keep that mantra in the back of your mind, and that will help you in kind of recognizing changes in potential energy. All right, so that's energy. We talked about that in chapter 1. Some new terms that we'll talk about here, things that we can actually measure, heat and work. And so heat, when we think about heat, that's just transfer of energy, where typically a temperature change is observed. And so we can calculate the amount of heat that is transferred through calorimetry, which is a section of this chapter. Next is work. Again, the physics definition of work is just force applied across some distance, all right? So work equals force times distance. But for chemists, the equation that we use when we think about work being done by chemical reactions is typically from gases. Gases expand or contract. So when we think about work in terms of chemical reactions, we actually think about changes in volume against an external pressure. Comparing this equation and the physics equation, the units work out. But the idea here is that work done by chemical equation or chemical reactions are typically made by changes in volume of that gas sample within there. So do keep that in the back of your mind. We won't really be using the work equals force times distance. We'll be using this one. And that negative sign is important here. I'll talk about that in a little bit. All right, and then finally, internal energy of your sample is the sum of all the kinetic and potential energy in your sample. So we need to think about these components separately, and then we can bring them together and think about internal energy in our sample. So let's use our intuition here a little bit. Well, actually, this is where I was supposed to do my demo. All right, where the hydrogen balloon goes off. All right, we hear the big boom, everyone covers their ears, and you go, wow, and you feel, okay, that chemical reaction produced a lot of energy, all right? So the idea here, bringing energy into this chemical equation, when we think about energy coming from a chemical equation, we use the unit of joules, right? This is the same joule as chapter 1. So the SI unit here is a kilogram meter squared over second squared. So do get used to seeing that unit here. And so the example here for the hydrogen balloon, we combined 2 moles of hydrogen, combined it with 1 mole of oxygen gas to produce 2 moles of water. And all of these are in the gas phase. I guess I forgot to mention that. And so the idea here is that this reaction produced a lot of energy, and I even say how much. As written here, this reaction produces 482 kilojoules of energy. But the thing is, where did the energy come from? We saw the energy coming off, all right? We observed that energy coming off, but we are the surroundings. So the chemical reaction actually lost that energy. So how we fully write this thermochemical equation is we write the chemical reaction here, the balanced chemical reaction, and we write negative 482 kilojoules. That negative sign indicates that this is an exothermic reaction, that the balloon lost the energy, and we saw that energy coming off. All right, so exothermic reactions here, where energy comes off, where we are the surroundings and we can see it, have a negative sign associated with those enthalpies, which we'll talk about in a later slide. All right, so do understand that this chapter you will be wrestling with a negative sign constantly. So let's use our intuition a little bit and think about, okay, let's think about these physical changes of water or whatever, and think about how does energy change to make these certain physical changes happen. So melting a substance, turning it from a solid to a liquid. Do we put energy into the sample, or do we take energy out of the sample? Let's just use our intuition. Into the sample. So is the internal energy of the sample, is it going up or down? Up, yes, because we're putting energy into the system. So this is a positive an increase in energy of the system. It goes up in order to turn a solid to a liquid or to melt something. All right, what about when we boil something, a liquid to a gas? How does internal energy of our pot of water here change? Also goes up. If you just think about it, you have to heat water to boil it, right? So in this case, energy also is going up in this example. And then finally, condensation. So the observation of seeing a gas turn into a liquid on the side of like a cold glass of lemonade or something. Do we think internal energy of that water, is it going up or down in that example? Yeah, in this example, it's going down. If we think about gas particles, they're much more energetic than liquid particles. So in order for that energy to change, we need to take energy out of the system in order to see that physical change of a gas turn into a liquid. So in that case, energy of our system is actually going down within there, those physical changes. So use your intuition a little bit there. So let's think about another example, but really look at the details of kinetic and potential energy for this scenario. So pretend we're boiling a pot of water. All right, so when we boil a pot of water, we're turning liquid water to gaseous or like water vapor, right? Steam. What temperature does water boil? 100 degrees Celsius. So let's think about water in that scenario. We're thinking about both the liquid component and the vapor component above it. All right, so let's compare that liquid water, right, the stuff that you see here, and the gaseous water above it. So if both of the liquid and the gas are at 100 degrees Celsius, so that's the idea, that they're both at 100 degrees Celsius, because that's how water boils. Let's compare kinetic energy and the potential energy of those two substances. So if you go back to the previous slide, kinetic energy is typically related to the temperature of your sample. So based upon all this information given to you here, if we compare liquid water and gaseous water, which one has the higher kinetic energy? Go back to the previous slide. Go back to the previous slide where we look at kinetic energy. Kinetic energy is the average kinetic energy of the sample is your temperature, is related to the temperature of your sample. So the idea here, if both of the liquid and the gas are both at 100 degrees Celsius, which one has more kinetic energy? They're actually the same because they are the exact same temperature. They are the exact same temperature, all right? So again, I tried to lead you into it here, that kinetic energy, it's related to the temperature of the sample. So they're actually the same because both are at 100 degrees. All right, so that's kinetic energy though, all right? So the idea is that the average kinetic energy of the liquid and the gas, they're about the same within there because their temperatures are the same. Now let's look at potential energy. So I'll write the equation for potential energy just so we can't kind of think our way through this. Potential energy of our sample is related to electrostatics, where the charges involved in the particles over the distance, that tells us something about potential energy. But typically what we see with particles and samples is that samples have low potential energy when the particles are attracted and they're close together. So let's think about the liquid sample and the gaseous sample and which one has more potential energy present. So let's think about our liquid and our gas. If we think about the liquid particles, are the particles close together or far apart? They're very close together. Versus our gas sample, they are far apart. All right? So in the liquid sample, shouldn't D be small? And then for the gas sample, D is a large number. So the idea here is that the closer the particles are to one another, the more attracted they are to one another. So we see a low value of potential energy. So in this example, because the liquid has a small distance between them, right? The particles are close together. Potential energy is actually going to be the lowest for the liquid sample. Versus for the gaseous sample, potential energy is higher. And so if we look at these different components here, kinetic energy is the same, but potential energy is different because we know to turn something from a liquid to a gas, we have to put energy into it. But that energy that we're putting in is actually going towards changing potential energy, changing how far away those particles are from one another. It's actually not going towards changing the kinetic energy or the overall temperature of the sample because that's water only boils at 100 degrees Celsius on Earth. And so all that energy we're putting into it is actually going towards potential energy, changing the distance, a liquid to a gas within there. So those are the details for something as simple as just boiling water, all right? And the idea of energy. All right, so let's talk about, energy in terms of what we think about in terms of physics and how chemists think about energy. Again, there's two components, kinetic and potential energy. So in this picture, we see the prototypical physics definition of kinetic energy and potential energy. Potential energy is energy due to virtue of position. So in this picture, what is this, a skateboarder or a snowboarder has really high potential energy, but no kinetic energy until they start moving along the slope that you see here. And so what you see as this person goes down, kinetic energy increases, potential energy decreases until they hit a maximum in kinetic energy at the bottom of the hill, but at the bottom of the hill, they have zero potential energy. And so the idea here, as they go, either side on this slope, we see kinetic and potential energy kind of swap places, all right? There's a transfer of kinetic and potential energy, but the total energy of the system typically stays constant, as long as, this is a frictionless plane and there's no loss of energy there. So that's the physics definitions of energy. All right, where we have this transfer of kinetic and potential energy within this scenario. Within chemistry, it's completely different. It's completely different. So these ideas of like physics and like skateboarders and snowboarders, like throw all of that out the window, because for chemistry, it's different. In chemistry, potential energy, just how we define potential energy is so different. All right, we use that electrostatics equation, but just in your brain, all right, just put like a little Post-it note in your brain that in chemistry, potential energy is lowest when particles are attracted and they're close together, right? So the whole idea of attraction and close together, this goes back to the electrostatics equation, Q1 times Q2 over D. So when I say attracted, I mean Q1 and Q2 are opposite charges, they're attracted. When things are close together, D is small. And so what we typically get are very low potential energies. And for chemists, a negative potential energy actually is possible, and it's actually preferred. Negative potential energies are preferred in chemistry, and that's not something you typically see in physics. So the idea here is when potential energy is zero, what that means is that the particles are neither attracted or repelled from one another. There's actually no interaction that's happening at all. So that's the significance of zero potential energy, but typically we want substances to have a negative potential energy. So we remember this graph, right? So we're going to use it again. So this graph is just the interpretation of the Coulombic attractions, the electrostatics equation we talk about when thinking about potential energy, where that electrostatic attraction is proportional to Q1, Q2 over D. Q1 and Q2 are charges of like two different particles, charges, and D is the distance between two of them. And so there's basically two types of scenarios that can happen. The particles can be attracted towards one another. So we can think like a positive and a negative charge. So when we have things that are attracted towards one another, we are at the negative portion of this graph. When we are talking about things that are repelled from one another, so either, two positive charges or two negative charges, we are actually at the top part of this graph. We actually will rarely talk about this top part of the graph. We will mainly be concerned about the bottom part where particles are attracted. That describes the majority of scenarios in chemistry. So we'll mainly be thinking about attractions. So we see that things are more attracted when they are close together, that the potential energy becomes more negative, versus if you bring them apart, two particles apart, whether they're attracted or repelled from one another. When they're far apart, you can think, oh, there's not much of an interaction occurring. So we see that graph approach zero in this case, when the particles are far apart, that there is no interaction. And that kind of makes sense, that the stronger the interaction, the closer they are to one another. So do understand how this equation gives us this graph, that negative potential energies are the most stable in our chemical systems we talk about. All right. So how does that have to do with, what does that have to do with chemical bonds and the idea of breaking and forming bonds? So again, think electrostatics here in our equation. So here I've just zoomed up on the bottom part of the graph, the part where we talk about attractions. Particles have the most negative potential energy when things are attracted and they're close together. So this relates directly into how we form bonds and how energy is involved in bond breaking and bond formation. When we think about atoms forming a bond, those atoms are close together, versus breaking a bond, the atoms are far apart. So thinking about that in terms of our electrostatics equation, Here, if we go down down the graph, we're forming a chemical bond, versus when we separate the atoms, when we break the bond, we're actually going up this curve, all right? So we break, we go up the curve. When we form, we go down the curve within here. Because thinking about how atoms are, how close they are to one another, whether they're in a bond or they're broken. And so the idea here, using the electrostatics equation, this is just the bottom part. This is still the same equation, Q1 times Q2 over distance, but in in this example, it's just attractions. Breaking a bond will always require energy, because what we're doing is separating the distance between those two atoms. We have to go up the hill. Or if you think about it just in general, if you want to break something, or if I want to break this expensive Apple pen, I have to put energy into the system to do that. And that's the same thing with chemical reactions. Breaking bonds always requires energy. Forming bonds always releases energy, because when we think about forming a chemical bond, we're actually going down the potential energy graph here. And so when we go down, all right, we're lowering our potential energy. We're becoming more negative. And so that energy is actually released out into the surroundings when that happens, when we form a chemical bond. That's because we're bringing two attracted particles closer together. These two things are always true. It always requires energy to break something. When we form a chemical bond, we always get energy back. We always release it. All right? And at the end of this chapter, I'm going to get on my soapbox and I'll rant for a while about that. Because biologists, you guys get it wrong, all right? Or you just make it a little too simple. So I'll get on my soapbox later at the end of the chapter. All right. Okay, breaking bonds requires energy. Forming bonds always releases energy, all right? And so that requires us to think about a reference point. Okay, when I say release energy, I mean the system is releasing energy, because we form that chemical bond, we become more stable, and the system releases that energy. And so we need to think about talking about and defining system and surroundings. And I already mentioned before, as humans, we're really selfish. We're really selfish, and we oftentimes think we are the system, but we're not the system. It's the chemical reaction that's the system. So in all these pictures, you know, kind of the people we're focusing on are the people in them. But to chemists, that's not the important thing. The important thing is actually the chemical reaction that's taking place, all right? So the boom that's happening there, that's the system. The thing that's in the Erlenmeyer flask, or the round bottom, the chemical reaction that's happening, that is the system. That's what we care about. Or whatever's in the beaker, that is the system. And in all these pictures, the people that we often think are the important thing, it's not. They're not. We are the surroundings. Oftentimes the observations we make are observations that have to do with the surroundings, right? I promise you, you're going to mess up the positive and negative sign sometime this chapter, but just remind yourselves, okay, I can't be selfish. I'm not the system. The world doesn't revolve around me. In all these examples, the chemical reaction is the system. And so we are the surroundings, all right? So the rest of the universe, except the system under study, is the surroundings. That often includes us, all right, as we are the surroundings. And so if you combine system and surroundings, that is what equals the universe, all right? So if you think about, you know, our chemical reaction, that's the system. We are the surroundings. So if we just add both of those things up, that's the entire universe. And so the first law of thermodynamics says that the energy of the universe never changes, right? There's no loss of energy and matter. It's not created nor destroyed. So we can utilize that idea and think about, okay, how does energy transfer from system to surroundings? Because oftentimes we can measure the surroundings, and so we can back calculate and think about, okay, how does energy change in relation to the system? So this essentially is the first law of thermodynamics, saying that between whatever is lost by the system is gained by the surroundings, because system and surroundings is the universe. There's no change in energy within the universe. So we will constantly be utilizing this idea that whatever's lost by the system is gained by the surroundings. But the problem is we need to be very cognizant of how we define system and surroundings in order for this to work. All right. So a couple ways of how we measure energy within system is how we define, system and surroundings. How is energy transferred between system and surroundings? How is matter transferred between system and surroundings? So we will mainly be concerned about this first one, closed systems. Closed systems are where matter cannot be transferred between the system and the surroundings. So in this piston, the piston is the system. Everything outside the piston is the surroundings. So in this example, matter, or like the actual chemical reaction, like the things involved in the chemical reaction, cannot escape the piston. All right, that's the idea that matter cannot be transferred, but energy can. And so energy can be transferred because this piston is movable. All right, that piston can go up and down. It can change its volume. So that's the idea that energy can be transferred, but not actual matter. And then open systems and isolated systems, again, we're just thinking, okay, can energy versus matter be transferred or not? We won't be looking at examples of those ones. We'll mainly be working around closed systems. And so this idea is, since energy can be transferred between system and surroundings, we can use the first law of thermodynamics and say that, okay, energy of the universe does not change, so we can see transfer of energy between system and surroundings, that whatever the system loses, the surrounding gains. Or the other way around, if the surroundings loses energy, the system gains energy, okay? We are the surroundings, so oftentimes the measurements we make we have to back relate to the system in some way. All right, so let's do an example. I've done enough talking here. All right, let's check our understanding of kinetic and potential energy. All right, so internal energy is E, the E. So internal energy of our sample, do you remember what that is? Internal energy? Sum, yeah, the sum of kinetic and potential energy. So let's just remind ourselves of that. So we got kinetic energy and plus potential energy. All right, so let's look at these two containers here. Which one has the greater kinetic energy? Kinetic energy is related to what observable? Temperature, yes. So which one has the higher kinetic energy? B, the hotter sample, yes. Yes, so remember, kinetic energy related to temperature. So we're just looking for the higher temperature here. All right. Potential energy. How do we think about potential energy? We look at the equation Q1, Q2 over D. And the two pieces of information on that little Post-it note on your brain says potential energy is lowest when particles are attracted and they are close together. All right, so that's when D is small, and we're talking about attractions here. So based upon that idea, which sample has the higher potential energy? A or B? A? B. Okay, remember, so samples have the lowest, most negative potential energy when they are attracted and close together. So the idea is in A, the particles are close together. So A has a very low, a very negative potential energy. Versus picture B, the particles are further apart. There's a larger D value within our equation here. So it actually has a higher potential energy. Okay, so yeah, again, Post-it note in your brain. Samples have the lowest potential energy, the most negative potential energy when they are attracted and they are close together. All right, so mainly the close together, because almost everything has attractions towards one another. So mainly close together. So greater potential energy will be B because they're further apart. All right, so based upon that, which one has the greater internal energy, A or B? B, yes, because if B has the greater kinetic and potential energy, if you add those two values up, right? It should be a greater value for B, all right, versus A. Because internal energy is the sum of all kinetic and potential energy. But if we just use our intuition a little bit here and think, okay, which one has the greater internal energy? A is a solid, a cold solid, and B is a hot gas. All right, and so kind of just using your intuition a little bit, you'll think that, oh, a gas sample, yeah, it's definitely going to have more energy within there. But if we think about the idea of like what kinetic and potential energy are, we get to the same conclusion. All right, just a little bit more roundabout way where we look at the specific details there. All right, so kinetic and potential energy. Okay, so the idea is we looked at the internal energy of these samples, these pictures individually. The problem is that it's very hard to actually measure the internal energy of a sample at a certain condition, all right? So it's actually, see how we didn't actually calculate internal energy at all? We just kind of thought about magnitudes. Yeah, the problem is that it's very hard to actually measure the internal energy of either of these pictures. But what we can measure is how much energy it takes to convert this solid to this gas. I can actually calculate that change in energy. So chemists, we can measure changes in internal energy for a process. So for this example, I would like to figure out, okay, what amount of energy is required to turn a solid to a gas. This energy I can measure, but the actual value for the gas sample and the solid sample, that's actually really hard to calculate. We're not even going to bother thinking about it. So we can actually measure changes in internal energy. We can't actually measure the values of themselves. So the idea is we're often going to be talking about changes in internal energy for specific processes. So in this process, we're turning a solid into a gas, for example. All right, so don't worry about the actual values for the final and initial condition. We just are caring about the process within here. So yes, so we'll think about the processes. We can actually measure that. So how we actually can measure changes in internal energy, all right? So mentioned again that this is the change in internal energy for a process where we have a final and an initial condition. Another equation that we can use to track the changes in internal energy for a process comes back to these new terms that I introduced, heat and work. So the amount of energy involved in this process is actually equal to the heat that's supplied to the system plus any work that the system, any work that is done on the system. So delta E, our change in internal energy, is equal to two different things, final minus initial, but it's also equal to Q plus W. This is the one that we will think about in terms of work and energy here. So internal energy, change in internal energy is equal to work plus heat in this case. So let's look at these two pieces of information separately here because we can measure both of them separately in terms of a chemical reaction. So Q is related to heat that is either given off or absorbed by a chemical reaction. So just to get our terminology right here, when Q is a positive number, all right, when heat is a positive number, we call this an endothermic reaction, meaning that the system gains energy. When Q is positive, the system is gaining energy. So it's Q of the system, all right? So the idea is endothermic reactions, Q is positive, the system gains energy. If the system gains energy, if we're holding the system and the system gains energy, what are we going to observe? It will get colder. Yes, the object that we're holding will get colder. All right, so endothermic reactions, they feel the reactions feel like they get colder, and it's because the system is gaining energy. The idea is, well, where's that energy coming from? It's coming from us, but we are the surroundings. All right, so get that in your mind, because oftentimes students will be like, oh, it's getting colder, that's a negative sign. I don't know why they think it's a negative sign, but I promise you will make that mistake sometime in this chapter, all right? Okay, so Q, system absorbing heat, all right, versus Q when it's negative means that the system loses energy. So what we observe a lot of energy coming off, being emanated from the actual system. So the system is actually giving off energy. We call this an exothermic reaction. So the balloon, the hydrogen balloon, that is a very highly exothermic reaction. We are seeing a very large negative Q because the system is giving off all that energy and we are observing it, right? Okay, so that is heat. So we use the terms exo and endothermic within there to talk about the sign. How is the system gaining or losing energy? Work is a little bit different here. So remember, for chemists, how we think about work, it's not a force times a distance. We actually think about gases expanding or contracting. So work of the system, and this will help you determine the sign, is negative pressure, the external pressure being applied on it, times the change in volume of the system. So the idea here is, if we know how the volume of the system is changing, we can determine the sign of work that is done by the system here. So I have that here. When the work of the system is a positive number, what this means is that work is done on the system. So what I like to think about it is like, if I have a balloon, all right, the balloon is my system. If I do work on, if I'm the surroundings, I'm doing work on the system, I'm like putting work by squeezing the balloon smaller, all right? So that's what you see here. A positive sign of work is related to a decrease in volume of the system. Do you see that? Right? So if you think about putting a like negative value in for delta V, don't you get a positive work out of it? All right, so that's how you can figure out the sign. So the idea is work is done on the system. I'm the surrounding, so I'm squeezing that balloon smaller, volume is getting smaller. That's a positive sign of work. Versus when work is a negative sign, the system does work. So that means the balloon, which is the system, does work on the surrounding. So I like to think, okay, if it's a balloon and it's kind of like pressing up against the system, or sorry, the surroundings, pushing up against it, doing work against, putting work into the surroundings. So what we see is a positive delta V value, that the volume of your system actually increases. System does work on the surroundings. So again, if you think about this equation, it'll get you the correct sign as well. That a positive delta V gives you a negative value for work. And so that is system does work. And so again, these signs will get you in trouble. All right, it'll get you in trouble. So let's do some examples here. Okay, so remember, change in internal energy, Q plus W. Be very aware of the signs. So you conduct some chemical reaction, it absorbs 25 kilojoules of heat and does 10 kilojoules of work. What is delta E? So a student who's not aware of signs, they'll just slap those two numbers together and say delta E is 35. Who thinks it's 35? It's not 35. We need to think about the signs of Q and W, because a lot of students will just think, oh, that's work, that's heat, I'm just gonna add them together because that's what delta E is. But what's not being indicated here are the signs of Q and W, all right? So the idea here is heat, all right? So 25 kilojoules of heat is being absorbed, all right? So Q is equal to, so think about this is Q of the system. Think about, is the system gaining that energy or is it releasing that energy? So how this question is worded, is that heat going into the system or leaving the system? into, because it's being absorbed. So is that a positive value or a negative value? That's positive. So in this case, Q of the system is in fact 25 kilojoules. Okay? If it said released, then it would be a negative 25. Okay. So if we think about, okay, here's my system, that means I'm putting 25 kilojoules of heat into it. Okay. But also we have this work component. So it says that 10 kilojoules of work is done on the surroundings. So we think about, is work a positive sign? Work of the system, is it a positive sign or a negative sign? It is negative in this case, because I like to think positive signs of work means that the system gains work. It has work done on it. That's how I like to think of it. So if the system does work, that means that is a negative sign associated with it. So negative 10 kilojoules of energy is done in terms of work. And so we can think, okay, negative 10 kilojoules of energy is leaving the system, that the system is doing work onto the surroundings. And so now we can add up those values here. And so we get that the change in energy of the system is equal to positive 15 kilojoules. So it wasn't as simple as just, boop, adding the numbers together. Nope, we got to think about the signs. All right, so in this example, the first one we just did, would you think the sample increases volume or decreases volume? Or do we not know? So work, the sign of work tells you whether the sample increases volume or decreases volume. All right, so remember, work is equal to negative pressure delta V. All right, so pressure will always be a positive number. And so you think, okay, what sign does delta V have to be to give me the correct sign? Delta V has to be a positive number, right? Yeah, has to do a positive number. And if we think about it, does work on the surroundings, that will happen when the system increases volume within there. So we should observe an increase in volume of this container, okay? So that's navigating that equation. So let's do one more scenario here. Let's consider this exothermic combustion reaction occurring in the piston of your car, in which scenario is delta E, change in energy of your system, always negative when the piston goes up or when the piston goes down. Okay, so we're actually using the exact same equation, Q, or delta E equals Q plus W. Delta E equals Q plus W. So this question is asking, in what scenario is delta E negative? When the piston goes up or down. So there's a piece of information given at the very beginning of the question. The very beginning of the question actually tells us the sign of one of the components there. I'm telling you what kind of reaction is happening. Exothermic. So does that tell us about Q or W? Q. And Q would be what sign in this case? Negative. Very good. Okay. So a negative number plus W, we're looking for a negative number. So in what scenario of work, what sign of work do we want in order for delta E to always be a negative number? Work is negative. Yeah, so if we have an example where work is negative, work of the system is negative, we will always have a negative delta E value. So the idea is, okay, which one of these options gives us a negative sign for work? When the piston goes up or down? If we think about it, when the piston moves up, does volume increase or decrease? Increase. When piston goes down, we see a decrease in volume, all right? So the idea is relate that idea to the sign of work. Work equals negative P delta V. So in order for work to be negative, delta V needs to be a positive number. So in which scenario will delta E always be negative? A or B? A or B? B, yes, when the piston moves up. Yes, because when the piston moves up, volume goes up, all right? So we see a positive change in volume. So if there's a positive change in volume times a negative value, work is negative. And so if we plug that back into this equation, and when work is negative plus a negative value coming from the exothermic reaction, delta E will always be negative, right? Yeah, when piston moves up because delta V goes up or is a positive number within there. I think that's when I want to write, when delta V is a positive number. All right, so do we see how all of these come together? Yes, work, changes in volume, exo versus endothermic reactions, yeah. So the question is, when the piston moves up, the volume increases, the internal energy of the system decreases. Only when there's a negative, a exothermic reaction that's happening within that piston. So the system is losing the energy, and it's transferring that energy to the surroundings to push your car forward, right? So that's why there's a negative delta E there, because it's taking that energy from the system, from the, combustion reaction happening in your engine, to pushing it towards, turning the wheels on your car. That's what that negative sign means there. All right, so let's do, all right. So the idea is we just looked at signs of delta E, changes in internal energy. This slide, I just want to mention the idea of changes of internal energy. The path that we take to calculate changes of internal energy for a process, the pathway we take doesn't matter. All we really care about are the initial and the final points of the process that's taking place. So the idea here is, like, I have a solid on the bottom here, I have a liquid up here, and I have a gas up here. So there's, solid, liquid, gas. So the idea is it takes some amount of energy to go from the solid to the liquid. It also takes a different amount of energy to go from the liquid to the gas, right? And so what the idea here changes in internal energy is a state function. What that means is that if we actually wanted to go from a solid to a gas directly, all we would have to do is add up those two amounts of energy, because the idea is that changes in internal energy is a state function. It doesn't matter the pathway we take. We can go straight from a solid to a gas, or we can go from a solid to a liquid, then to a gas, and it requires the same amount of energy to go in that stepwise function within here. So these two processes, if you add them up, is the same amount of energy to go straight from a solid to a gas. That's the idea that changes in internal energy is a state function. This is going to allow us to do a lot of manipulation in terms of calculations with Hess's law, where we will look at ways we can manipulate enthalpy, because that is also a state function, and help us with calculations within there. All right, so this is actually the last time I'm going to talk about changes in internal energy. All right, so internal energy is the sum of kinetic and potential energy. I already mentioned that it's actually very hard to calculate and determine like an actual number for internal energy. So we utilize the idea that on Earth, pressure is always constant on Earth. It's always 1 atmosphere. So what that allows us to do is kind of ignore the work component done in chemical reactions, and we can just focus on the heat component of chemical reactions. And so if we just focus on the heat component done on chemical reactions at a constant pressure, we can think about energy in terms of enthalpy instead. So this is a capital H instead. And this is, the reason we can do this is because most of the chemical reactions we do on Earth are done at constant pressure. because the pressure on Earth is always 1 atmosphere. So any heat that's gained or lost under constant pressure, which is on Earth, is related to changes in enthalpy. All right, so from here on out, we'll talk about the idea of changes in enthalpy, delta H, and that is directly related to the amount of heat that is gained or lost in chemical reactions. So the idea of the sign of energy, like positive or negative, the sign of Q, positive or negative, exo or endothermic, they still apply to the idea of delta H in this example as well. So we still use the terms endothermic, all right, to mean positive Q values or positive delta H values, and exothermic is related to negative delta H values. And the idea here is that delta H is also a state function, so we can relate the delta H's for these different processes, solid to liquid, the enthalpy for the change from a liquid to a gas, and that will be equal to the transition of the process from a solid to a gas. So we're just replacing the word internal energy with enthalpy instead. That's essentially what we're doing here, and we can do this because most chemical reactions we do on Earth are happening at constant pressure. So, excuse me. So when you look up enthalpy values for chemical reactions, and you see these delta H values, this is the amount of heat that is generated or absorbed by these chemical reactions that you see. So when we think about thermochemical equations, what that means is we have some type of balanced chemical equation plus a enthalpy term associated with it. So the great thing here is we can actually still treat these thermochemical equations like we have done with stoichiometry. And it works just like that, and I'll show you an example here. But the idea is with enthalpy and the direction and the magnitude of energy that's involved in these chemical processes, this is an extensive property, meaning how much energy is generated from chemical reactions. It matters how much stuff we start with. If we think about if we have a full tank of gas versus a half tank of gas, there's less energy output if you have half a tank of gas because there's less matter there. So the idea here that we already looked at this chemical reaction. 2 moles of hydrogen plus 1 mole of oxygen gives us 2 moles of water. 484 kilojoules of heat is given off by this reaction. So if we cut this reaction in half, all right, so if we look at these 2 reactions, see how I just divided it by 2, how will the enthalpy change? Also divided by 2. So the delta H for this new reaction on the right side here is how much? How much energy can be produced here? Negative 242 kilojoules. Because we divided the reaction in half, we have to divide that enthalpy value in half as well. All right, because enthalpy is an extensive property. All right, well, what if we reverse the reaction? What if instead of blowing up the hydrogen balloon, all right, reacting hydrogen with oxygen, what if we split water? What if we took water and we split it into hydrogen atoms and oxygen atoms? So if we think about, how is this reaction different from the previous reaction, we actually reversed the chemical reaction. All right, so if we reverse a chemical reaction, we actually have to change the direction of energy input. When we blow up the hydrogen balloon, energy is released. So if we reverse the reaction, energy is no longer going to be released. It actually has to be absorbed in this case. So what we do is actually change the sign of delta H. So for this chemical reaction, do we know what the delta H value is? Positive. Positive what? 484, yeah, because what we see is if we compare the original reaction and the new one, we just did the reverse of it. So it's a positive 484 kilojoules of energy. So this reaction actually requires energy. You have to put energy into the water in order to get the atoms or the bonds here to split, all right? And so what we'll see here is that these energy values in these thermochemical equations, I didn't actually write the states of hydrogen and oxygen here, but those states are important. You'll see if there's different states, we'll have different energy values here. So relating delta H to stoichiometry, it works exactly the same. So if we balance this chemical reaction, so it's the combustion of methane, I think we need a 2 in front of water and a 2 in front of oxygen, and then we have 1s here. So this chemical reaction, I tell you, produces 890 kilojoules of heat. So that means that delta H value is negative 890 kilojoules. All right. So remember how we did stoichiometry? We had to be in the unit of moles of stuff. Right? So if I'm in moles of methane, I can relate that to 1 mole of methane is 2 moles of oxygen, will give me 1 mole of CO2, which will give me 2 moles of water. So the same idea when we add this energy component, it still applies. So 2 moles of water, if we produce 2 moles of water, we also produce 890 kilojoules of heat. If we burn 1 mole of methane, we also give off 890 kilojoules of heat. So I'll finish this problem on Wednesday. So have a good Monday, y'all.